Okay, so we already discussed before that how polymorphic viruses work. What would be the strategy for antivirus solution to both detect complicated polymorphic viruses and also cure them? In general, I'm aware about two major approaches. One is based on combination of signature plus AV scripting. In some examples, it might be just purely scripting. So as I mentioned, antiviruses would usually have some embedded scripting language or even compiled scripting language, which they would be able to interpret and execute some extra logic. The reason for those languages is the main body of antivirus, the main software, is compiled in binary. And that binary is updated on some basis, but not on an hourly or daily basis. It might be updated once a month because it needs to pass certain verification, compliances, QE, and so on, right? So you always want to have updatable part in antivirus. Those updatable parts would be signatures, which could be updated on a weekly and daily basis, and at some point they even reach the hourly basis update. And also scripting languages. So because a scripting language would not be a binary code, it would be interpreted code. It would be much easier to test, and also potential bugs in this code would be much less detrimental to the whole engine, right? Because it's just the engine which interprets it already tested. It's just the code which is going to be interpreted, which is updated. That scripting language, what it would allow, either in combination with the signature or even without the signature, for the scanning engine, identify, for example, entry point, and start searching for some anomalies. And that anomalies can be long jumps, it could be jump on the entry point by itself, or it could be some signature or some combination of weird instructions. Because while polymorphic engines would try to generate the code as different as possible every time, they would also include a lot of noise in the code, a lot of instructions which would not make sense. For example, incrementing or decrementing the register, which then not used. And that's something you could encode in the scripting language, the algorithm which would quickly verify, does the code make sense, right? So instead of just applying a signature on the first 20 bytes or 100 bytes or 1000 bytes from entry point, the malware analyst would write a script which would analyze that first 100 bytes from the entry point, or maybe it would analyze the first few jumps after the entry point and analyze area around those jumps to find, is there any presence of known polymorphic engine? Because even the polymorphic engines, again, they would generate pseudo-random code, it would still be pseudo-random, so you could find certain patterns. So the code would analyze the areas, and then if something suspicious detected, for example, this jump would have an address, right, where jumping. And so the code would say, okay, let's inspect some code around here, and it would start inspect this code, and then of course it will find another jump, and it would inspect that code as well. And the goal for the script would be not just to detect that it is a malware, because that could be relatively easy to do, but it also needs to recognize and confirm, hey, what kind of polymorphic engine it is. The easiest way to do it would be to find certain patterns. For example, as you say, it's a decryptor, it meaning it has a key inside to decrypt the payload. And this key would consist of multiple immediate values. Maybe they sum together, maybe they incremented on every byte, or there's some sort of logic. So there are two things we want to extract from this decryptor when we analyze it. We want to extract key, and we want to extract location of payload. We would look for the key, and that might be consist of combination of different instructions, right? It would not just be like one instruction, it might find a multiple. And also we would try to find either address or some sort of reference to where the payload is. So as soon as we find both, or we think we find both, what it would do, it would try to decrypt using the key and decompress that payload, and then apply the signature on that decompressed payload, right? So it would be, we would decompress certain number of bytes, and we assume that, again, as I mentioned, in polymorphic viruses, the payload would not be polymorphic. So we would assume that we actually know the payload, so we would decompress it, decrypt it, and say, okay, does it match the signature? And if it does, then now we know that's the polymorphic virus which we were looking for. Because the engine, the anti-malware engine, could have hundreds of signatures, the hundreds of scripts like this. They're going to be regularly updated, because polymorphic viruses, polymorphic engine would be regularly updated. But that's only one half of the solution. Now we know it's a polymorphic virus. We even identify what kind of polymorphic virus, because we extracted the key, we extracted location, it all matched. How to cure this? Second challenge this script has to solve is that somewhere here there is also that compressed original benign code which that virus patched, stored, and original entry point. So the script need to analyze the rest of the code to find original entry point and find the payload and reconstruct them to clean up the virus. And that would be how anti-malware solution would both detect the polymorphic virus and also cure the polymorphic virus using some combination of signatures and scripting languages. There would be more advanced polymorphic viruses which would not just simply patch something in the beginning of the original entry point or change the entry point. They would disassemble a bunch of functions and would find some area inside to put the jump. And the problem is that jump here, right, it can be actually not very close to entry point. It can be above, it can be below. It all depends on what actual benign code is doing. And that makes it pretty hard for just a scripting language to find that patch, because we don't want to scan the whole file, and there are probably thousands of different jump instructions in the file. Yeah, it could be very tough to find that location. And that's why another approach, to more advanced approach to detect this, would be x86 emulation plus script, and probably plus signature as well. The script itself would most likely contain a part of the signature, but to be fair enough, that would be a kind of threefold combination. It would be emulation, scripting, and signature. And the way it would work, the emulation engine would start emulate the code from the beginning, including jumping the jumps, all the whatever jumps are in the code. And would try to emulate as far as it can get every jump on every change, like major change of location from entry point, right? And then there might be one jump, we executed some code, and then there is another jump, we executed some code, and there is another jump. And when I say jump, by the way, I also mean call instruction as well. Like, it kind of can be substituted. I know that assembly wise it's different, but what I mean is the change of EIP register, right? The change of the address of where the code executed. It would emulate these jumps. Every time it does change that location, it would inspect the code, right? Does code have any anomalies which potentially look like polymorphic engine? The logic which would inspect the code very often, again, would be implemented as updatable script, because as you know, polymorphic engines change and gets updated, so you cannot just write it once, compile it, and now you have universal polymorphic engine detection. So you need some sort of updatable way to detect them and detect anomaly in the code. So that's what script would do. So the emulator would emulate the code, script would analyze the code on the maliciousness, and again, now because we do have emulator, we can analyze the code, we can apply certain signatures on the code, and as soon as we detect, okay, that is probably a polymorphic engine, again, same strategy. We need to find a key, we need to find location of payload, and we need to find a cure, like how to cure. And as soon all of that executed, the binary is cleaned, detection and cure is successful, we can move on to the next file.